All right, welcome to the Selected Homework Problems video. I hope you are ready and attentive, just like October is ready and attentive. She is ready to learn. She is ready to do some practice problems and see how things are going to go. Hopefully you are ready as well. Hopefully you don't step on my tablet. So let's do some problems. And we're going to start with number 94 in the textbook. Most of the problems we're doing here are the more complicated ones. We pull up 94, which is somewhere. It says use direct substitution to show that each limit leads to something called an indeterminate form, 0 over 0. We'll talk more later in this quarter about what indeterminate form means. Basically, it means it means a form that doesn't tell us anything. All right, then evaluate the limits. All right, so let's look at the limit as x approaches 2 of x minus 2. X minus 2 divided by x squared minus 2x. All right, so again, if we try direct substitution, that would give us 2 minus 2 divided by 2 squared minus 2 times 2. Oh no, my attentive student has left. And she's sitting in my chair. That's also not okay for a classroom environment. Can't just leave the class and sit in my chair. Well, then the top becomes 0. The bottom becomes 4 minus 4. Yes, this does become 0 over 0. So direct substitution doesn't work. Even though it's a rational function, direct substitution doesn't work here. The problem told us to use direct substitution to show that we have 0 over 0. We've done that. And then it says evaluate the limit. So this is one of those 4 techniques that we talked about. How do we change this to something that we can use direct substitution on? And we're going to factor it. Limit as x approaches 2 of x minus 2 divided by the denominator. As a common factor, we can take out an x. We're left with x minus 2. And then as long as x is not equal to 2, we can cancel. If x is equal to 2, then canceling changes things. But again, x is not equal to 2. It's approaching 2. It's getting very, very close to 2, but it's never quite touching. So we can indeed cancel here. So this is going to be the limit as x approaches 2 of 1 over x, which we can evaluate with direct substitution to be 1/2, because 1 over x is a rational function. And the denominator is not equal to 0. That's our answer for 94. Let's do 110 next. Assume that the limit of f as x approaches 6 is 4, and for g it's 9 as x approaches 6, and h it's 6. Use limit laws to then do 110. That's the limit as x approaches 6 of h of x cubed over 2. We need to use limit laws, and we know that the limit for h is 6. So we'll evaluate with limit laws. Limit laws says that, okay, notice that something divided by 2 is the same as multiplying by 1/2. We can use a constant multiple rule. Say this is a limit, 1/2 times the limit as x approaches 6 of h of x cubed. This is our constant multiple rule. Don't remember what the constant multiple rule is? Look up either in the top of the section in the textbook or with the handout on Canvas. Next up, notice we have an exponent, a power, that's a positive integer. Integer, -1, -2, 3, 5, these are all integers. Positive integer says that we can use the power rule. This is going to be 1/2 times the limit as x approaches 6 of h of x cubed. So instead of taking the limit of something cubed, we can take the limit of that thing and then cube that limit afterwards. And now we know that this limit equals 6. So we know that this equals 6. And again, this is the power rule. And we can use that power rule. It does require that it's a positive integer, but we do have that. You need 1/2 times 6 cubed, and now it's just algebra. I think it's 108. 6 cubed should be 216. Half of 216 is 108, I think. You let me know if I'm wrong. That's how we do 110. Scroll down to 116, piecewise functions. Use a calculator to draw a graph and study the graph to evaluate the limits. So you could do this by hand. Let's do this graphically. If you don't remember how to graph piecewise functions, you came to the right place. So it's x cubed minus 1 for negatives and 0. We're going to say g of x equals x cubed minus 1. Wait, was it plus? X cubed minus 1. So for piecewise functions, to restrict the domain, use brackets, less than or equal to, type the less than, and then type the equal to on your keyboard. 0. So it's a cubic function to the left of 0. And to the right of 0, to the right of 0, it's just always equal to 1. The g of x is just equal to 1 if x is bigger than 0. So to the left of the 0, it's that cubic function. To the right of 0, it's that constant function. This is the piecewise function. I'm actually going to change the color. Hold down the mouse. Click on blue to show that it really is the same function. All right, it just behaves differently on one side as opposed to the other. And if we really want to get technical, we should add open circles and closed circles. You don't need to do this next part, but there's an open circle at positive 1. Right? This point up here is not included. This is only if x is strictly bigger than 0. So again, you hold down, you click, you go to blue, open circle, and there's a closed circle at 0, negative 1. And again, hold down the click to make it blue. This is what the piecewise function looks like. I'm not forcing you to, since this is just for you to see how things work. You don't have to copy this graph down. All right. But if you wanted to graph it better, that's how you would do it. Get those open circles and closed circles. So 116 is saying, okay, graph this. We did that. Study the graph to evaluate the limits from the left and the right. Well, the limit as x approaches 0 from the left of this function, and the limit as x approaches 0 from the right of this function, what can we say about these? And again, in this case, it doesn't even turn out to matter which one's open and closed, because for limits, it does not matter the actual function value at that point, only as you get really close. So as we get really close from the left, we're always on this piece. We get really close from the left, what are we getting really close to? Getting really close to this point. As we approach from the left, we get really close to negative 1. As we approach this function from the right, and we can zoom in, this is a constant function. So as we approach 0 from the right, it's always just positive 1. And again, the two-sided limit does not exist here. It's not asking about the two-sided limit, but if we did want to know about the two-sided limit, we'd say the two-sided limit doesn't exist because it's different from the left and the right. It's gonna, in the future section, we're gonna end up saying that this function's not continuous, because for something to be continuous, we'll talk about this in the next section, the two-sided limit has to exist and it has to equal the function value. But this one doesn't even have a two-sided limit. Okay? And that's what we've got right here. And that's number 116. Let's do 120. Use the following graphs and limit laws to evaluate each limit. The limit as x approaches 0 of fg over 3. So let's use limit laws. First off, before we can even use limit laws, we have to make sure that the limits of f and g at 0 exist. So at 0, oh, I should not have clicked. At 0, yeah, the limit exists for this function. At 0, it looks like the function approaches 1. When x is 0, the function approaches 1. That's f. For g at 0, yeah, the limit exists. Function looks like it approaches, I don't know, maybe like negative 2.5 or something. It's a little unclear. But the limit exists. So the limit exists, we can use limit laws. Limit laws say this is going to be 1/3 times the limit as x approaches 0 of f of x times g of x. This is the constant multiple law. Dividing by 3 is the same as multiplying by 1/3. And then, because both limits exist, we can then use the product law as the limit as x approaches 0 of the first function times the limit as x approaches 0 of the second function. The limit as x approaches 0 of that first function, we said was about 1. This first function is approaching 1 as x approaches 0. And the limit as x approaches 0 of the second function is maybe like negative 2.5 or something. You can approximate this. Since I'm approximating, I'm going to change this equal sign to an approximately equal sign. And we'll get an answer. That's about negative 2.5 over 3. Not a great answer. Write this. It's combining decimals and fractions, which is not so good. Negative 2.5 is negative 5/2. This becomes negative 5/6 about. Two more examples here to include in this nice little video. Let's do 128. Squeeze theorem. Evaluate the limit using the squeeze theorem. Use a calculator to graph when possible. The limit as x approaches 0 of this function, where we have a piecewise function. Limit as x approaches 0 of f of x, where f is a piecewise function. It's either equal to 0 or x squared. It's equal to 0 if x is rational. And x squared if x is irrational. So this is a bit strange. Remember rational and irrational numbers. Rational numbers are numbers that can be written as fractions. Usually numbers with repeating patterns, although that's not precise definition. Irrational numbers are numbers like pi, numbers like e. Another example of an irrational number is 01, 001, 0001, 00001. I'm pretty sure that's an example of an irrational number. And then like ... so on. Okay, so this cannot be graphed. This cannot be graphed. They're an uncountable number. These are both infinitely many things, but one of them is uncountably infinite. And you get it definitely can't be graphed. It's pretty wacky. But can we use the squeeze theorem? So to use a squeeze theorem, first we have to say, we have to find two functions that bound f. We want to look at two functions that squish this function in the middle. All right. And specifically, we want two functions that squish this function that are easy to work with and have the same limit. So kind of a natural choice here is maybe 0 and x squared. So this is what my gut says to choose. And it's true, but we have to make sure that this is useful too. So, right, the function is always one or the other. X squared is always positive or 0. So that's the biggest. It's always going to be positive or 0, and this is always going to be the smallest. So this is true. The question is it useful? As x approaches 0, how are these two things behaving? Well, as x approaches 0, well, that's always 0. And as x approaches 0, okay, so they're going to the same place. Squeeze theorem is a squeezing here. So we're going to say, this is remember, there's two things we need to check for the squeeze theorem. You can look at your notes to see the two things. This is one of them. We need to bound our function between two other functions, and we need those two other functions to go to the same place. And the limit as x approaches 0 of the lower function, that's equal to 0. And that's the same thing as the limit as x approaches 0 of the bigger function. This is a polynomial. We can evaluate this with direct substitution. So these are the two things we needed to check. 1 and 2. Check, check. So by the squeeze theorem, the limit as x approaches 0 of our original function, the one we care about, is also equal to 0. Because it is getting squished between two other things that are going to 0. And that's how you can use the squeeze theorem for a more complicated problem compared to the one from the notes. The last video of this whole section is going to be 130. Still haven't figured out, by the way, why the textbook sometimes jumps around when I alt-tab out. The density of an object is given by its mass divided by its volume. The Greek letter rho is equal to m divided by v. Again, this is, This is density. It's a Greek letter rho. And this is mass. And this is volume. Use a calculator to plot the volume v as a function of density. So if we solve for v, right? If we solve for v, multiply both sides by v and then divide by rho, you're going to get v as m over rho with a little bit of algebra. And the book gives this to you, right? It gives it to you right here. It wants you to plot this, assuming we're looking at something with a mass of 8 kilograms. So if something is a mass of 8 kilograms, we're going to v is equal to 8 divided by rho, and it wants us to plot this. We go over here and say v equals rho. It actually tells us, it does theta for us. It does not do rho for us. V equals our variable divided by 8. Sorry, 8 divided by our variable. We'll use x here because Desmos is not too happy about rho. All right, we've done that. You don't have to copy it down here unless I tell you that I want you to. Evaluate the limit of this volume function. And again, this is function notation down here. F of x is usually how we write it. Here, this is v of rho. So can also write v of rho. It's kind of like the same thing as writing f of x. So evaluate the limit of this function as our variable approaches 0 from the right. The limit as rho goes to 0 from the right of this function v of rho. Well, graphically, that's not too hard. It's just a reciprocal function times 8. As our variable is getting close to 0, look at those x values. Those inputs are getting close to 0. We're going to the left. Close to 0 from the right side. Well, the function's going off to infinity. And then it says also that it wants us to interpret what this means. As rho, as the density, right? This says as the density of something goes to 0, and negative density doesn't make sense. So as the density goes to 0, again from the right, as the density of something, as something gets less and less dense, what's happening to the volume? So if something is 8 kilograms, and we're making it less dense and less dense and less dense, well, the volume has to be growing and growing without bound. And that's going to be our answer. So if we were to like type it out or something, we'd say like for a mass of 8 kilograms, as the density decreases to 0, the volume increases to infinity. Volume grows without bound, or increases to infinity, however you want to say it. This is like a good answer, but I'm not too picky about this, but this is what it's wanting you to say. Because this is the relationship between density, mass, and volume up here. So if the mass is 8 kilograms and the density is getting really close to 0, the volume has to be going off to infinity. Number 129 is actually really, really cool too. But that one is for you. Let me know if you have any questions, and have a good time.